Welcome. Let's see heat with infrared thermography. Inside a fired heater, energy never stops moving. Flames heat the tubes, and the tubes heat the process fluid. But heat that lands in the wrong place, hot spots, coking, flame impingement, is exactly what consumes tube life. Infrared thermography lets us watch it happen, while the furnace runs. To read an IR image, we first need to understand how heat moves. Heat moves in three ways. Conduction, particle to particle, through solid metal. This is how heat crosses the tube wall. Convection, carried by a moving fluid, flue gas sweeping the convection bank, process fluid inside the tubes. And radiation, electromagnetic waves that need no medium at all. Watch the rings spread from the hot body, they cross empty space. In a fired heater, radiation is the dominant player, flames and glowing refractory pour radiant energy onto the tubes. And here is the beautiful part, radiation is exactly what an infrared camera can see. The furnace broadcasts its condition, optically, every second it runs. 3 mechanisms, 1 system, and each one leaves a visible thermal signature. Every object above absolute zero glows. Not necessarily with visible light, but with electromagnetic radiation. The hotter the body, the higher the intensity, and the shorter the peak wavelength. That is Wien's law. At furnace temperatures, 800 to 1200 Kelvin, that glow sits in the infrared, invisible to our eyes, but perfectly placed for an IR camera's detector. Now watch what happens as the body heats up. The Stefan-Boltzmann law says radiated power grows with the fourth power of absolute temperature. Double the temperature, and you get 16 times the radiated power. Small temperature differences become large signal differences. That extreme sensitivity is why infrared imaging sees hot spots so clearly. So how does the camera turn radiation into temperature? The hot object emits infrared waves. A special lens, germanium, because ordinary glass blocks IR, focuses them onto a microbolometer array, thousands of tiny detectors, each one reporting its own temperature. Watch the thermogram build, pixel by pixel, every pixel is a measurement. One warning though, emissivity. A shiny, polished surface reflects its surroundings and reports a falsely low temperature, while an oxidized surface, emissivity around 0.85, tells the truth. Know your surface before you trust the number. But a furnace is full of fire, and flames blind the camera with their own radiation. The trick is a narrowband flame filter. At about 3.9 micrometers, hot combustion gases are nearly transparent. Filter everything else out, and the flame effectively disappears, the camera sees the tube metal behind the fire. That is how instruments like the FLIR GF309 measure true tube skin temperature, through flames, up to 1500 degrees. Step back and look at the whole furnace. Fuel energy enters the firebox and splits into 2 streams, useful heat absorbed by the tubes, and losses through the stack and the casing. The radiant section transfers most of its energy by direct radiation, the convection section recovers what it can from the flue gas. Infrared thermography audits this balance tube by tube, from outside, with zero shutdown. Now the subtle part, and it fools many people. Heat flows from the fire, through coke, metal, and scale, into the process fluid. Coke and scale are insulators, each resistance drops temperature. So compare the 2 tubes. The bare tube, the surface reading is close to the real metal temperature. The coked and scaled tube, the outside reads cooler, 700 degrees, while the metal underneath actually runs hotter, 920. Remember this paradox: on a scaled tube, the cold spot is the hot spot. Read the image naively, and you will underestimate the metal temperature, and walk away from a tube that is quietly consuming its life. Let's look at real data, from an actual GF309 survey on furnace 3H0101, in an ethylene plant. First, the modeled pattern inspectors call giraffe necking, across the tube coils. Each patch is a temperature anomaly tied to internal coke or external scale. Next, a circled hot spot at 1478 Fahrenheit, about 800 degrees Celsius. Then, spot readings across the modeled tubes, up to 699 degrees, with inefficient zones flagged. And finally, an area measurement peaking at 967 degrees Celsius. Every one of these images was taken through the sight glass, while the furnace was on stream. The findings: Fire Box A at 1041, Fire Box B at 1037, against a design of 1100. Near the limit, creep accelerates sharply. The response: trend with repeat surveys, verify with ultrasonics, and check remaining life against API 530. Heat always leaves a signature. Infrared lets you read it, before it becomes failure. Thank you for watching.